Hello everyone, I am Karthikeyan Thirumalaisamy. Today I will be presenting my work on cloud native defense and depth security for mission critical services in managed Kubernetes. This presentation focuses on how mission critical services can be securely deployed in managed Kubernetes environments. Let me walk you through the key topics I'll be covering today. Here's the roadmap for today's talk. I'll begin with an introduction that sets the context for why Kubernetes security is important, especially in managed services like AKS, EKS, and GKE. Next, we will define mission critical services and explore examples from industries like finance, healthcare, defense, and supply chain. Then I will highlight the security challenges in managed Kubernetes, such as insider threats, runtime exploits, and misconfigurations. We will move on to the cloud native security, 4Cs: cloud, cluster, container, and core, which form the layered defense model. We will then look at practical security measures for each layer. First, the cloud boundary, then cluster boundary, container boundary, and finally the core boundary. At the end, I will wrap up with key takeaways. Kubernetes has become the foundation for modern cloud native infrastructure. It allows organization to deploy and scale applications efficiently. Most enterprises today use managed Kubernetes service such as AKS, Azure Kubernetes Services, EKS, Amazon Elastic Kubernetes Service, and GKE, Google Kubernetes Engine. While these managed services simplify operations and reduce management overhead, they also introduce new security risks, especially for sensitive or mission critical workloads. For example, control plane exposure, misconfigurations, or insider threats can have serious consequences in these environments. To address these challenges, the work, this work proposes a defense in depth security model based on 4 C's of cloud native security: cloud, cluster, container, and core. Each C represents a layer of defense that builds on the one below it, creating a defense, creating a comprehensive layered protection strategy. It helps the system more secure. Now that we have set the context, let's take a closer look at what I mean by mission critical services and why securing them in Kubernetes environments is so important. In this slide, I define what I mean by mission critical services. These are software systems that are absolutely essential to an organization operations. If they fail, the business faces major financial, safety, or reputational consequences. For example, in finance, this includes payment processing platforms or fraud detection systems that must operate securely and continuously. In healthcare, mission critical systems include electronic health record platforms and medical monitoring software that directly affect patient care. In defense sector, we are talking about secure communications and intelligence analytical systems that must remain confidential and resilient. And in the supply chain, examples include system responsible for code signing, security scanning, and package verification. Each of these use cases handles sensitive or regulated data, so deploying them in a managed Kubernetes environments demands an extremely high level of security. Now we have understand what mission critical services are. I will move on to discuss the security challenges organization faces when deploying them in managed Kubernetes environments. Now let's look at some of the key security challenges that arise when deploying mission critical workloads in managed Kubernetes environments. First, there are insider threats from administrators, whether they are cloud admins, cluster admins, or tenant admins. Each level has privileged access, and if any credentials are compromised, it can expose sensitive workloads. Second, misconfigurations and weak authentication are very common. Simple mistakes like using overly permissive roles, public control plane endpoints, or missing encryption can open up large attack surfaces. The third the third attackers can inject malware into containers. This can happen through vulnerable base images, compromised registries, or during the CI/CD pipeline. exploits and privilege escalation allow attackers to escape from containers and gain control over the host or cluster resources. Finally, supply chain compromises are becoming more frequent. Adversaries target build systems, image registries, or dependencies to insert malicious code before deployment. These challenges highlight why managed Kubernetes security requires more than just the default protections offered by cloud providers. We need a layered defense in depth approach. Now let's talk about the defense in depth of security architecture, which forms the core of my proposed model. The idea here is simple but powerful. Rather than relying on a single layer of protection, we apply multiple layers of controls across all four domains of cloud native security: the cloud, cluster, container, and core. Each of these layers reinforces the others, creating a cumulative defense that significantly reduces the chance of successful attack. This model also follows the zero trust approach, which means every request, user, and workload is verified, regardless of whether it is originates inside or outside the environment. By enforcing the zero trust principles at every layer, we can prevent unauthorized access and lateral movement within the Kubernetes environment. This layered security design helps mitigate key risks such as insider threats, supply chain attacks, and runtime exploits, which are common in managed Kubernetes environments. What is also important is that this model leverages built-in security integrations available in managed services, meaning organization can strengthen their security posture without adding excessive complexity. Next, I will begin breaking down this architecture by layer, starting with how to secure the cloud boundary, which is the outermost layer in the 4Cs model. This section focuses on securing the cloud layer, the first C in the cloud native security model. The hub spoke network topology provides centralized control and visibility. The hub virtual network manages routing, inspection, and security policies, while spoke virtual networks isolate workloads for stronger segmentation and reduced risk. Strict firewall rules are applied to restrict both inbound and outbound connections. Only authorized communication paths are permitted, reducing exposure and limiting potential attack vectors. Together, these measures establish strong perimeter protection. They minimize external exposure, shrink the attack surface, and enforce zero trust principles at the network boundary. Together, these measures establish strong perimeter. Using private clusters and endpoints ensure that control planes and container registry communicate only through internal IP address, keeping sensitive management traffic off the public internet. With the cloud boundary secured, the next layer of protection focuses on cluster boundary, where access control and internal communication security become critical. Before we talk about the next C, let's quickly recap what security gaps still exist after the first C, cloud. The cloud layer focuses primarily on securing the external network boundary. It provides protection from internet-based threats through firewalls, network segmentation, and control connectivity. At this stage, all inbound and outbound communication is monitored and validated to ensure that only trusted traffic flows into or out of the Kubernetes environment. However, this protection is limited to the network perimeter. While it successfully reduces the exposure from external actors, it does not address risks that exist inside the environment. The next layers, cluster, container, core, contain components that remain vulnerable to internal threats, privilege misuse, and runtime exploitation. Therefore, deeper security measures are required to harden these inner layers, which will be defined in the following sections of the architecture. The next focus area is the cluster boundary, where the goal is to protect the internal components such as API server, etcd, storage, nodes, and interpod communication. Securing cluster boundary represents the second layer of defense in the cloud native security model. On this layer, the focus shifts from external network protection to securing internal Kubernetes components such as API server, etcd storage, kubelet, and pod communication. First, a private API server combined with RBAC integration limits control plane exposure. By using private endpoints and enforcing strong authentication with role-based access controls, only authorized users can interact with cluster resources following the principle of least privilege. Next, etcd storage, which stores all the cluster configurations and secrets must be protected. Encrypting etcd data at rest using key management service KMS ensures that even if storage is compromised, sensitive data remains inaccessible. To protect kubelet and node access, anonymous access should be disabled, ports restricted, and network policies applied to prevent unauthorized interaction with node-level services. Implementing network segmentation through Kubernetes network policies or cloud-native firewall limits pod-to-pod and namespace communication, effectively reducing the lateral movement within the cluster. Finally, OPA, Gatekeeper Admission Controller, enforces compliance and policy rules before workloads are admitted. Examples included blocking privilege pods, ensuring image signatures, or verifying configuration standards together. These controls strengthen the internal security posture of Kubernetes environment by safeguarding its most critical management and operational components. With cluster layer secured, attention now shifts to next layer. What security gap still exists after the second C cluster? At this stage, both the cloud layer and cluster layer have been secured. The network perimeter is protected, and strong controls such as private endpoints, RBAC, encryption, admission policies. However, these controls primarily protect the infrastructure and management components of Kubernetes, not the workload themselves. The next major security challenge lies within container layer, where vulnerabilities can still be exploited even in a well-secured cluster. Attackers may attempt container breakouts, exploiting kernel vulnerabilities, or injecting malicious code in running containers through compromised images or runtime downloads. The following section explains how confidential VMs, confidential containers enhance container isolation and prevent host or admin level tampering. Securing container boundary. This section focuses on the container boundary, the third layer in the cloud native defense in depth model. While the cloud and cluster layers are addresses external and control plane threats, the container layer deals with risks inside the workload itself. Pods and containers are risk of breakout or kernel exploitation. If a container is compromised, it can potentially escape to the host, exploit kernel vulnerabilities, or move laterally across workloads, threatening the integrity of entire cluster. To mitigate this, confidential virtual machines (CVMs) are used to protect node-level workloads. CVMs utilize hardware-backed trusted execution environments (TEEs) to encrypt memory and CPU to isolate a virtual machine from hypervisor and host, preventing unauthorized access from infrastructure layers. Building on that, confidential container extend this protection to individual containers. They run inside secure enclaves, ensuring that application code and data in use remain protected, even if the kernel, container runtime, or host is compromised. Together, these confidential computing technologies prevent host or admin tampering, ensuring that even privileged users, cloud operators, or compromised system components cannot access or alter the sensitive workloads. This approach brings a new level of assurance to running mission-critical services by safeguarding the runtime environment from both external and insider threats. With the container boundary secured, the next focus is on the final layer. Before that, let's recap what security gaps still exist after the third C container layer. At this point, most of the external and infrastructure layer threats have been mitigated, as you can see in this picture. The protections from the hypervisor, host, or guest agents, pods or containers are already in place through confidential computing and strong isolation controls. However, the remaining risk lies within the code itself, the application logic running inside the container. Even with the strong TCP, trusted computing base, provided by the confidential containers, the code that executes at runtime can still introduce new vulnerabilities. Examples include code that downloads external packages, spawns unauthorized processes, or executes unverified scripts at runtime, all of which can bypass intended security boundaries. This residual risk highlights the need for controls that protect not just the container environment but also the behavior of the code running inside it. The next and final layer, the fourth C code, addresses this exact gap by applying runtime integrity controls, system call restrictions, and continuous monitoring to security ensure secure execution. So the following section explains how the code layer uses measures like trusted email signing, immutable containers, seccomp, and fault code to completely mitigate the runtime threats. Securing code boundary. The code boundary represents the fourth and final layer of the defense in depth model. This layer focuses on securing the code that executes inside containers to ensure that runtime behavior remains controlled and trusted. First, using trusted image registries and signing ensures that only verified and cryptographically signed container images are deployed. This step significantly reduces supply chain risks by preventing the use of unverified or tampered images. For Linux workloads, the distroless image provides an additional safeguard. These images do not contain shells, package managers, or other utilities that attackers could exploit, reducing the attack surface to only components required for the application to function. Next, immutable containers prevent any modification after the deployment. If updates are needed, a new image must be rebuilt and redeployed, ensuring that runtime tampering or unauthorized changes cannot occur. The seccomp security feature adds another layer of protection by restricting system calls that processes or mounting file systems, etc. Seccomp helps block malicious runtime actions. Finally, Falco provides a real-time runtime monitoring. It continuously observes container and system, detecting anomalies such as privilege escalation attempts, unexpected file access, or the execution of unknown processes. Alerts are generated whenever the suspicious behavior occurs. Together, these security controls ensure that the code running inside the containers remain verified, immutable, restricted in behavior, and continuously monitored, effectively closing the final security gap in 4C's model. With all four layers, cloud, cluster, container, and code, secure, the defense in depth architecture now provides comprehensive protection across the entire Kubernetes environment. What security gaps still exist after the 4C code? At this stage, the defense in depth model has fully implemented. Every layer from cloud to code now has its own set of protections. With immutable containers, system call restriction, and real-time monitoring in place, the code layer effectively closes the last known gap. At this point, there are no remaining vulnerabilities within the defined layers. All the major attack surfaces from infrastructure to runtime have been addressed. The overall security posture becomes significantly stronger because each C reinforces the one below it, forming a continuous chain of trust. This means that even if an attacker somehow breaches one layer, the remaining layers continue to protect the system. In other words, the combination of all four layers, cloud, cluster, container, and code, delivers a comprehensive end-to-end defense model for mission-critical workloads. Next, let's move on to the key takeaways, where I will summarize the benefits of this defense in-depth approach and how it enables strong protection without compromising the developer agility. Key takeaways. So, to wrap things up, here are the main points I want to leave you with. First, mission critical services, whether it is payment system, healthcare applications, or defense workload, need more than basic protection. A defense in important to remember that the default cloud provider security, things like IAM, firewalls, and network rules, is only part of the story. Those features are great, but they don't fully address modern multi-layer attacks that target the supply chain or runtime environments. That's where the real strength of defense in depth comes in. By layering controls across all four C's, cloud, cluster, container, and code, and combining that with zero trust, confidential containers, and runtime monitoring, you can close every gap from infrastructure to application. In short, defense in depth gives us a way to protect mission critical workloads without slowing down innovation. That's all for today.